Earlier this year, 9 scientists died during an unexpected eruption on a volcano in Colombia. One of them was Geoff Brown of the Open University. His death was ironic, as his method of predicting volcanic eruptions and thus saving lives has only recently received universal recognition. Fellow scientists recall a man of many qualities.
Diplomatic.
A burst of energy. A very pleasant companion.
The triumph and tragedy of a great scientist. Geoff Brown remembered at 2:35.
Every year, people die because of volcanic eruptions. After every eruption, people ask, why couldn't it have been predicted? This is the story of a scientist who gave his life trying to do just that.
Hello there, my name's Howard Stableford. At the moment I'm filming on location with Open Forum in Siena. Now, as a TV presenter, I recognise that one of the great privileges of my job is visiting fascinating places like this and meeting extraordinary people. Well, one filming adventure I'll never forget happened not too far from here on the slopes of a smouldering Mount Etna in Sicily, and with a man who understood the moods of the mountain like few others. That's right. Now, I'm rather interested to know just how dangerous it is working at the summit of a live volcano.
Well, it can be quite dangerous if there's a big explosion of magma and so forth that happens whilst you're up there. But you know, if you're fairly careful, I think you can get by. So
and we'll be careful.
We'll be pretty careful today. Yes.
Good, I'm looking forward to it.
Right. Well, a group of us from the Open University Geophysics group are up here on Etna measuring gravity, and we're on the edge of the summit craters. It's actually 7 o'clock in the evening and the sun went down about an hour ago, and we're here in the moonlight, freezing and watching some rather spectacular fireworks coming out of one of Etna's central craters. This is known as the chasm, and it literally is a chasm. It's about 200 meters deep, and right down in the bottom is a hole that's glowing. It's glowing red with red-hot magma, several meters across, and the whooshes that we can hear is gas escaping through this hole from a larger body of magma that's in the feeder pipe underneath.
A few days on the volcano and weeks, sometimes months, spent doing calculations and then writing it up. Such is the life of the research scientist.
John, you got the height data yet for station 3 on Etna for this year, please?
Station 3, you say? 2961.8533.
From the first paper that we published together in 1984 to the most recent one that came out in early 1993, Geoff and I worked on about 15 active volcanoes such as Poas, Etna, Askja, Krafla, in 6 different countries. What we did was to set up microgravity monitoring networks at each of these volcanoes.
Okay, I'm at station D2. It's down by the crater lake. Can you see me?
Okay, find your line up, please.
Poas volcano, Costa Rica in Central America.
Okay.
I'm Plum. Can you see me?
Okay, Hazel, thank you.
Okay, I'm ready.
Shot it one more time. I'll plunge if you are able to plumb up in again in a few minutes.
Altogether, some 50 stations like this are surveyed before the next stage in monitoring the volcano can begin, measuring gravity.
It's stupid since the vandals bent the pin over, isn't it?
Yes, the Poas vandal.
This will look quite sharpish since it's getting dark.
dark by the time we're out of the crater.
Within the box is a spring balance, 45,000 pounds worth. It's 100 million times more sensitive than kitchen scales. It's used to measure gravity very accurately indeed. One gravity meter provides a cross-check on the other, because the measurements are right at the limit of the instruments. They can measure minute variations in gravity caused by tiny changes in the volcano's mass, such as those caused by the rise and fall of hot magma in the vent of a volcano.
Sounded like a geyser.
Small geysers up there.
Is it still going?
Bit steamy there.
Back on Etna, Geoff took me to see some spectacular remnants of old eruptions.
Those are incredible walls of rock. What are they, Geoff?
Well, they're what we call dikes in geological parlance, and what they really are is vertical curtains of magma that has congealed in cracks that were formed by extension. So you can imagine a wall of this Valle del Bove in which we're standing being pulled apart, and the magma comes up, congeals within the cracks. But before it congeals, it may well have fed lava flows at the surface, so there may well have been lava flows up above us. And so you can imagine the whole of this area was dikes and lavas in the past, and of course it's collapsed away and it's gone out towards those villages down there.
Routine checks of gravity readings revealed the first indication of a future eruption on Etna for Geoff and Hazel.
Yes.
2873. 0.595.
All microgals different.
A sudden increase in gravity meant hot magma was approaching the surface. It turned out that these were early warning signs of the largest eruption on Etna for 300 years.
So where do we go next then?
Station 6.
Okay, station 6.
Looking at this photograph of the summit region of Etna, we can see these fractures that opened up in 1989 coming down from the summit towards the southeast. This is the region where we had the largest gravity increases, down here. So it's obviously the most exciting region where something is going on beneath the ground. And it was this section across here that we decided to put into the computer. We can actually see the dimensions of some of these dikes by computing them this way. This is a dike, this red one here, that was intruded sometime between June of 1990 and June of 1991. And we have the feeder pipe here coming up to the summit of the volcano, feeding the dike from great depth down there somewhere. It's rather hard to see in 2 dimensions on the screen, so if we look at the model here, we have the magma feeder pipe here coming up inside the volcano towards the summit. It's more or less cylindrical and it's about 50 meters across. And the dike comes off from that here about 3.5 kilometers, but it's much more narrow. It's about 4 meters across. So putting that against the silhouette of the volcano itself, we've got the summit region here and the southern flank. And if you follow along the propagation of the dike here, the top of it, where it intersects the topography, that's where the 1991 eruption began.
The dike broke through the flanks of the volcano and spewed lava into the Valle del Bove at the rate of 10 cubic meters a second for 16 months. Gravity data obtained by Geoff Brown and Hazel Reimer had predicted the exact spot where the main eruption occurred on the 14th of December 1991. Prior to eruption, the behavior of the magma was complicated, but the gravity data provided a picture of what had been going on.
So we're beginning to understand how a volcano like Etna works. We saw precursors to this eruption. And that's just what Geoff Brown was doing on Galeras volcano earlier this year.
Setting up gravity stations on the explosive volcanoes of Central and South America is particularly hazardous. Geoff, climbing to the highest station on Arenal, a volcano in Costa Rica. All around are fallen blocks thrown out of this overgrown firework. Fortunately, the volcano degasses fairly regularly, and the risk is a calculated one. The Colombian volcano, Nevado del Ruiz, dormant for 150 years, erupted in 1985, causing a mud flow which destroyed the town of Armero. The official death toll was estimated at 25,000 people. Nestling beneath another Colombian volcano is the town of Pasto, and it was to this volcano that Geoff Brown and a team of international scientists came in January this year. Characteristically, Geoff gave a television interview on the volcano before he went down into the crater.
Ok, porque fue necesario hacer buena exposición de geofísica.
Ah, yes, I understand. It's necessary to make a good geophysical and geological investigation in Colombia.
After. Especially
after the eruption in 1985. The volcano, Galieras, covers a large area around Pasto. For this reason, a decision has been made to spend 10 years investigating this volcano.
Decisión para la década. Sí.
Collecting baseline data that could be used in future hazard assessments was the main reason for the international team's visit to Galieras and for their conference at Pasto. 4 months later, at a meeting in Brussels, one of the group who went to Galieras was a scientist from Iceland. He describes what happened on the volcano on the 14th of January.
We went in 6 groups up to the volcano. This was a scientific conference. The volcano had been quiet for 6 months, and in our experience, before any event, volcanoes usually rumble. They can be detected on seismographs or other monitoring devices, and there was a lot of monitoring devices on Galieras. So it was actually without hesitation that the group went on the top of the volcano, and even the group that wanted to do some measurements went into the crater. So the explosion came absolutely unexpectedly. There was no human possibility actually to foresee it. And well, describing feelings, it's very difficult. I was already down at the foot of the volcano where it happened. And when the reality really started to dawn on us, I only remember some numbness of mind. I mean, when you realized the tragedy that had occurred.
Right. What kind of eruption was it?
That also is a bit difficult to explain. Probably there was some accumulation of gases in the throat of the volcano, which gradually increased in pressure until this relatively small explosion occurred. The accident was that people were actually standing on the crater wall when the explosion occurred. Had nobody been there, it would have been a small explosion which certainly had not created much attention by anybody.
So why is it necessary for scientists to go so close to the active vent?
Well, these 2 types of measurements which were being made on Galieras that day was one, to sample volcanic gases which were emitted from fumaroles within the crater. These gases you can only sample by entering the crater. The other was that Geoff Brown, he wanted to make detailed map of the gravity field of the volcano, and that's why he was standing on the rim of the crater when it occurred with his instruments. It was not possible to do this by any other means.
9 scientists died on that tragic day on Galieras in January. Should they have taken the risk? A fellow volcanologist.
It wasn't really a dangerous thing to do under the circumstances. Obviously, if you're a volcanologist working on a volcano, you have to take risks, but it's important to calculate the risk that you're going to take. And in Geoff's case, if you actually work it out, it was something like a 1 in 5,000 chance. So he was very unlucky.
Geoff took that risk because he believed it was necessary. Another volcanologist and colleague, Peter Francis.
The humanitarian aspect of Geoff's work was twofold. The first, he was interested in predicting volcanic eruptions, and that's an obviously important task because so many big cities are located just at the foot of volcanoes. That's exactly what he was doing in Colombia when he was killed. And the second was the environmental effects of volcanoes. Many volcanoes produce huge quantities of toxic gases which go a long way downwind from the volcano, and they impact the environment around the volcano quite severely, with some important implications for the people living around the volcano.
People at Etna knew him very well, and he was always welcome. And I think the work he has carried out during years, throughout some years, has been of great importance for the safety of property and human lives.
Geoff was a great believer in the international effort on volcano research. One group was supported by the European Commission in Brussels.
We were very sad this morning in this meeting at the European Community, the first one with our team since several years. Geoff has been one of the principal promoters of volcanological research in Europe. And the most important contribution was this very promising relation between gravity anomalies and the activity of the volcano. He has opened a way that we are all engaged in pursuing in the future.
J'ai rencontré Geoff Brown la première fois sur les bords du cratère du Poas.
Yes, I met Geoff Brown for the first time on the edge of the Poas crater in Costa Rica. And I think that the gravimetric measurements that Geoff was doing in Costa Rica were a completely extraordinary achievement in volcanic research. He had made really the first precision measurements of gravity linked to eruptive phenomena, and his results are the best, and they will remain the best.
Well, one of Geoff's great strengths was that he was a very diplomatic person, and this is something which is absolutely essential if you're coordinating and running large international research programs. And I think Geoff was an expert at keeping everybody happy and making everyone feel as if they were actually part of the team.
One example of teamwork involved scientists at the Royal Observatory in Brussels. Bernard Ducam.
From the discussion we had with many volcanologists in Europe, from Iceland, Italy, Spain, and of course Great Britain, we felt that one of the major problems in monitoring volcanoes is that we should need to have more measurements made continuously closer to the active zone of the volcano. It means that we must have cheap instruments, so we can install a lot of them, and also instruments that are running quite automatically. And it seems that there is a lack of those automatic recording systems that could be installed and left alone for several months on the volcanoes.
So, continuous monitoring of very small gravity changes on a volcano is on its way. But what about ground deformation? The tiny changes in the topography that can take place as magma swells the volcano before an eruption. Can this measurement be made remotely too? On the observatory roof, there's a special receiving antenna, linked with a second antenna a few hundred yards away. These can be linked with a network of other antennae and a time to receive a signal from a satellite compared. From the times, you can work out the distances, and the result is an extremely accurate global positioning system known as GPS.
GPS system is now a fantastic tool to monitor any deformation of the ground in, let's say, very remote and difficult areas, and with an accuracy better than 1 centimeter. And at the end of this year, we shall install first permanent station close to the summit on the Etna in Torre del Filosofo, where we shall have 1 tidal gravimeter and also 1 GPS recorder to monitor at the same time the gravity changes and the ground deformation. We have gained already much experience on Etna with Geoff Brown, and we are very confident that in the future we shall be able to continue his work.
Back at the OU, infrared data from a satellite gives a picture of how the lava moves.
This is a part of a Landsat satellite image showing the eastern part of the island of Sicily. It's just south of Italy. And we have the coast here of the Mediterranean Sea on the right looking black, some clouds on the left looking white, and all this blue is the snow on the high ground, including the summit and the flanks of Mount Etna. But the eruption starts low down on the flanks and runs from here down towards the town of Zaffarana. And what we're seeing here glowing in red and orange is the very, very hot part of the lava flow.
Again, this illustrates the potential of monitoring volcanic activity without risk. Detailed analysis of the Landsat image was used to work out where the lava would end up and was a factor in the decision of how to block the flow. Wearing his other hat, Geoff was head of the Earth Sciences Department at the OU. On the 1st of February, the Earth Sciences Wolfson building was opened.
As you all know, there is a dark shadow of sadness over today's ceremony. 2 weeks ago, Professor Geoff Brown, the head of the Earth Sciences Department, was killed by a sudden eruption of the Galeras volcano in Colombia. Geoff Brown gave his life trying to save the lives of others, and we grieve for him. His life and career as a teacher, researcher, and leader in this academic community epitomized the very best of the Open University.
Well, for me, Geoff led by example. He was active in teaching, he was active in research, he was active in the university through his chairmanship of the research committee. So basically, he led from the front, and that gave people confidence. And despite all those activities, he always had time to talk to people as individuals, to share their problems, and to try to help them. So for all those reasons, he'll be very sadly missed.
To me, he was the ideal head of department. He was the first head of department when I came here as Vice-Chancellor to invite me round, and had a flair for interesting me immediately in what they were doing. But later, as I got to know him better, I appreciated the way he combined that with a tremendous readiness to serve on university groups or special task forces I would set up, and so combine a university perspective with obviously a tremendous defense of his very powerful department.
If it hadn't been for Geoff Brown, I can safely say that none of this equipment would probably have been in the OU. One of Geoff's first actions as chairman was to try to develop an initiative to bring stable isotopes into the Department of Earth Sciences. And in doing so, he came across me. And probably he bit off a little bit more than he could chew, because instead of bringing in one mass spectrometer to do stable isotopes, he's acquired a group of 20 people and 10 mass spectrometers.
But despite the politics of university life, or maybe because of them, Geoff always enjoyed teaching.
Geoff used to like places as remote as this in Derbyshire, and I'm here at the moment remaking an OU television programme for the Physical Resources course. And it's a bit weird to be doing it on my own, because 10 years ago, Geoff and I were making this programme together. He was a good teacher, perhaps because he enjoyed teaching. And I remember running a couple of field courses to the Lake District, and he was never perhaps happier when he was teaching on an outcrop like this, surrounded by a group of OU students.
And that should be the last word, but not quite.
A man like Geoff Brown, who had so many abilities in so many different areas, you can't really sum up in one word. But if I had to choose one, it would be multifaceted.
Unselfish.
Considerate.
Unpredictable.
He was an eternal optimist.
He could never say no.
Très agréable.
A great scientist and a friend.
A very pleasant companion.
Diplomatic.
A burst of energy.
Geoff Brown was a man who was able to create cooperation between men.